Kirkwood Math. Hi, it's Mrs. Fogg. I'm going to guest video today in Miss Kirkwood's class. I'm really excited because I love this lesson. So we're going to learn today about translating absolute value functions and equations. But first, we're going to do a little refresher of what translating means using step functions. So we have this problem here where Uptown Sandwich Shop is increasing the number of bonus points in its reward program. And I look over here and it tells me I get 1 point for each dollar I spend and 5, I need to annotate. See, I'm talking to the computer already. Here we go. And 5 points for each time I visit. So right away, I start thinking of this as an algebra equation. I'm going to get 5 points and then not 2 times, 1 point for every dollar I spend. Okay, and there's no fractional points. So if I go to the sandwich shop in the past and I spent $3.80, that's 3 bonus points plus 5. That would give me 8 bonus points. So they're going to increase the number of bonus points by 2. Okay, meaning I'm still going to get for the dollars that I spend. But instead of getting 5 bonus points for each visit, I'm going to get 7 points. So my sandwich and what they want you to see is just this constant value is changing by 2. So everything in my graph is going to move 2 value or 2 points or 2 spaces up. And we're going to look here. I don't want to save my annotations. It's going to take a minute to say no. Okay. And so this is a solution. This is kind of what I just talked about over here where I was writing. And they used a graphing calculator here, but I think you can see, I want you to see here. That's fine. I just want to, she's talking to me. Okay. What I want you to see here is if you see, this is where the original step function was graphed, and then everything moved up to. So that's really what we're talking about when we're talking about a translation or a transformation. It's how does the graph differ from what we had to what we're going to have. And that's what we just talked about. Oh, we got to move this guy. Oh, no, I can't. We're going to pause.
Don't worry about that first try it for that example 1. We're going to go ahead and look at this next example.
So we're going to talk about how does adding a constant value to the output affect the graph of f of x equals absolute value of x. And we're going to use this term. I'm going to use this term called parent function. So f of x equals absolute value of x is our parent function. There's no extra letters, numbers, values, etc. Oh, wow, we have a lot of stuff here. So in this case, we're first going to compare absolute value of x minus 4 with absolute value of x. And you'll see they put a g of x here. That's just so we can compare the two functions. So when we have a number or a value outside or behind our absolute value bars, this is our new graph. So you can see the graph in red is our absolute value of x minus 4. If I were to change that to, they show the next example here of x plus 2, move my graph. Slightly too far. I think you get the point. That x plus 2 is going to sit.
You have to do a big circle.
I wanted to dot right there. There is going to sit at a y value of 2. So as we move this, sorry guys, I'm learning how to use the board at the same time. We can see that that value there moves our graph up or down. Okay. So in terms of what you should have in your notes, we want you to look at this part here.
And you're going to be writing this in that gray section of your student companion.
Okay? And I know there's some gobbledygook, so let's talk about what this says. It says g of x equals the absolute value of x plus, and then there's a k. And yes, you have to use the letter k for this. We'll explain why in a little bit. Translates, so moves the graph of f of x vertically. If you're not sure what vertically means, it means up and down. So to recap, you have absolute value of x. If you have a plus and then a k value, your graph is going to move up. And if you have minus k, your graph is going to move down. The axis of symmetry, meaning this line in the middle, your axis of symmetry does not change.
All right, so go ahead and see if you can apply what we just talked about. In your textbook, do number 2, A and B, and for each function, identify the vertex and the axis of symmetry for these two functions.
So now we're on our next example, and our question starts off the same. How does adding a constant to the input affect the graph? So let's look at what we've done with this one. Now, you'll notice we still have that -4, but that -4 is inside the absolute value bars. If you remember on the prior one, the -4 was outside the absolute value bars. And you can see our original graph is the blue one. Our new graph, is this red graph. And you'll see that it says x -4, but it's sitting at a vertex of +4. That's weird. So let's see what happens if I move my slider to say x +4. What do you think's going to happen? And undo the pen. Undo the pen. Okay. Can't see my drawings now. So if I go x +4, you get the idea. It's not exact. You get the idea. It's now sitting at a vertex. Go back to my tape. Hold on. There we go. So x +4 is actually sitting at a vertex of -4, 0. So let's look at what they're saying here. The value of x minus h translates this original graph, or this parent function, horizontally by h units. So this is the part that's confusing. If h is greater than 0, the translation is to the right. If h is less than 0, the translation is to the left. If you want some typical speak, what I always say is the vertex, I should be typing this, got my bad handwriting here. The vertex moves in the opposite direction of the sign. Moves, even if you can't read this, you can listen to what I'm saying, in the opposite direction of the sign. Mrs. Kirkwood really wants to type.
You can't.
Yes.
You can't read it.
She's laughing, but you can't read it. My point is you shouldn't be reading it. You should be listening to me. The vertex moves in the opposite direction of the sign. That's the math gobbledygook for if h is greater than 0, the translation is to the right, and if it's less than 0, the translation is to the left. Or you can just have fun with the slider here. Yeah, see, even you pressed the wrong thing. So when it says x minus a value, the vertex is actually in positive land. And when it says x plus a value, the vertex is actually in negative land.
And so if you need to pause and go back and write all this stuff down in your notes, please do that, because these are the important little pieces you need to know to solve your problems. Take your notes and try 3A and B.
So earlier in the video, I told you that this number outside the absolute value has to use the letter K. And the number inside the absolute value has to be at H. So your vertex is going to end up sitting at an X value of H and a Y value for K. Let's look at some problems and that'll make some sense. And I got to unannotate so that I can show you this. Okay, so if you look at this problem, compare the graphs to the parent function. So I have X minus 4, which remember, that's going to be opposite. So X minus 4 minus 2. So this is going to move 4 to the right. Should have had her type this. And down, use arrows, 2. Okay, and you can look at that red graph. It moved 4 units. The vertex was originally at 0, 0, the parent function. It moved 4 units right, 2 down. If you look at the next one, does that say negative? That says 5, 1. So I have to unannotate. So this is going to be, X plus 5 is actually going to show up as, and then plus 1. So it's going to move it 5 units to the left and up 1. Oh, you get the point. I can't get there exactly. You get the point. So I'm going to highlight here for you, which you can write in your notes. The value of H in this parent function translates the graph horizontally, that means side to side, and the value of K translates it vertically. So if we're going to type, and now Ms. Kirkwood is going to type for me because she knows how to do this, okay? So H moves your graph left, right, and K moves your graph up, down. And then this very bottom line here, let's see if I can highlight now, says, it gives you that vertex there. And you want to use H and K because you are going to see H and K in lots of different non-linear equations and functions for the rest of your math career.
All right, so take what you learned and do problem 4, A and B.
So now you'll notice we have the letter A in front of the absolute value. And in this point, A is going to be your slope. And it's very similar to what you're doing on the warm-ups this week, where you're talking about how does your slope affect it. So we look at 2 examples here. The first one is our blue line was the parent function, and our red line is the function with a slope of 1/2. And so you'll notice that that gets wider. Actually, I want me to use the slider here. And if it gets greater than 1, it gets narrower. So here's a little bit of confusion. You have 2 terms called vertical stretch and vertical compression. You want to type them for me, Ms. Kirkwood? She's so good. So vertical stretch is actually when the graph gets narrower, and vertical compression is when the graph gets wider. So I always use the example of if you take a rubber band, put it on the table, put your finger down on it, and then pull the rubber band up, you are stretching the rubber band, but the rubber band will get tighter and closer together.
And this is something that we probably did backwards in class, so we're pointing it out here, and then I will show you in class that the rubber band thing in case you're having trouble with it in your head.
Okay, so if you also need notes, can I scroll down to that? I don't know how to do that. Oh, see, we're on the wrong thing. Oh my gosh, we have 14 minutes, we have 30 seconds left before we're out of time. Okay, so if you're taking your notes, these are the notes you want to have. When your A value is in between 0 and 1, the graph is a vertical compression. When it's greater than 1, it's a vertical stretch. And then the other thing is if it's negative, it's going to open down.